Welcome to this lecture of the course Digital System Design with PLDs and FPGAs. In the last lecture we have seen the behavior of the controller and the structure of the controller, how to design the controller and so on. So before going further about some timing analysis and the design, let us run through those slides very quickly. We have seen in the slide an example of the CPU, and as I said, the controller job is to give control signal to this data path, and we have taken an example of instruction adding A and B and putting the result back to A, the execution part of it, but that is enough to kind of enough for analysis. So essentially it means moving A to this register, B to this register, and selecting the operation and moving the ALU output back to the register A. Now that each movement involves enabling, giving a latch signal, and upon the clock it moves, and disabling. So this is achieved by giving a pulse, same pulse to enable and latch. With respect to clock, you have a certain timing with respect to clock, and then when the clock comes it is transferred, then it is disabled. Same thing to B enable, latch, and the clock comes, it is transferred and disabled. At the same time give the addition code here. As I said, there are various units. Through a multiplexer output comes, and right state gates are there at the output of multiplexer. The enable signal of that is this one. So you give this enable signal, A latch, and the clock comes, it is transferred and it is disabled. So that is what is there. Move A to TR1, which has a macro step which is enabling A, giving latch signal, and the clock comes, it transferred and disable A, everything is done. Moving B to TR2, selecting ALU operation, and then moving ALU back to the register A. So basically I said that the possible timing waveforms are shown here. The enable and the latch, corresponding latch, get the same signal. A enable, this one latch, B enable, 2 latch, ALU enable, and the register A latch. And as I said, this waveform itself is a pulse for the first duration of the clock, second duration of the clock, and third duration of the clock. It is little bit shifted as if it is a kind of cooking up the waveform, so that the clock edge comes when the latch is high. And I said this looks like little bit of manipulation at this stage, but we will see how in practical circuit this comes very naturally and it works effectively. So the question is that how can we generate these pulses, what kind of circuit can be used. Definitely this cannot be from a combination circuit, because some input like add AB code gives to a combination circuit, it cannot produce a sequence. So it has to be a sequential circuit, and the question was that whether we can use a counter to generate this. So assume a counter counts every clock period like 0, 1, 2, then it is enough at the 0th count a pulse is generated for these two signal separately. At the count 1 this is generated, at the count 2 this is generated. So at least for this part of the game a mode 3 counting is enough. So that is what we have shown. You have a mode 3 counter which counts 0, 1, 2. You put a logic here to look at the present state or the count and decode, like when it is 0, 0, 2 signals will be 1, when it is 0, 1, other 2 signals will be 1, and so on. So we write the truth table of this, then you like the input is the present state, Q1, Q0, outputs are these set of signal. Definitely this has to be repeated, okay. For convenience I am showing it together, but assume there is a separate column for A enable and TR1L. It is not that it is tied together, but this happens only for this instruction, maybe some other instruction it cannot be together, but just for the convenience I have shown like that. And so here this particular signal is a function of the present state. So we say output is a function of the present state. So we decode, we put an output logic and then decode the output as a function of the present state. That is how we generate these pulses. Then the next question was that is it generic, that you have some crazy pulse requirement for the controller to work, then this structure can it produce. So I have shown some example, not maybe a realistic instructions waveform, but let us assume put some random thing and try whether it can work. So here you need a pulse in the first clock period and the third one. In the second one you need second and third, and in the third set you need in the third clock period. So as I said, it is easy. Say the first signal is nothing but the decode of 00 or decode of kind of 10, and the second one is a decode of 01 and 10, which when minimized you get Q1 XOR Q0. So it really doesn't matter that you just whatever the output logic is changed for various decoding to produce the required output. That is all what is required, and this structure so is quite generic and it can be used for any kind of controller. That means you design a controller for a multiplier, divider, or some other any application, then the same structure is used. Only thing is that depending on the need of these various transition, various inputs and outputs, the next state logic changes for the various transition and the output logic changes for the various output in each step, because that we have a sequence or states this controller is going through, and we produce at each state various output as and when required, and the sequence itself is in terms of the clock period. So that is very important to understand. Everything is in terms of the clock period. The granularity of the controller is in terms of clock period. We can the least step, the smallest step we can do is in a clock period. That should be understood. And another question is that whether we do this machine need to count 0, 1, 2. We don't care, it can count 2, 1, 0, only that the logic is changed. So normally when we design a state machine, we are worried about the inputs, the transitions and the output, and we are not very much worried about how this counter counts, and itself this is not a very, in a complex case it is not a very sequential kind of state change. Maybe depending on some input it branches to various state, and there it further branches to some state, come back to locally, come back to the original state and so on, depends on the application. So the state transition can be very complex, and so we don't care about the state, nor we can assign some meaningful, like we cannot start saying that 0, 1, 2, 3, it makes no sense. So that problem state assignment, and the controller is also called, as I said, finite state machine, because it transits through the number of finite states for the whole operation. So it is called finite state machine or FSM, okay. So that need to be understood. So and ultimately, so we said that it is the counter need not be ordered the state. So we have a step called state assignment. So when you normally work, we work on symbolic state, at the end we assign numerical state, and this can be manually done by the designer, or tools can do. Maybe you can do state assignment in such a way that maybe this one of this logic is minimized. Sometime it is used to solve some timing issues. All that we will see later as we progress, and essentially when you are designing an FSM, we have some specification, some timing waveform, and we translate that into basically some inboard state transition, that means sequence of states, and in each state what are the outputs, that is what we are going to design, and from there we can derive the next state table and the output table. So we start with the specification in terms of description and waveforms, then we work out that waveform into this inputs, state transition and output, and ultimately we work out the next state table and the output table. Then the structure is known and we can design the controller. So basically that is what is the finite state machine or a controller. There is a counter part which need not sequentially count, it goes through various states, various steps, various sequences, and at each sequence, each step, some output is decoded, which has which does a lot of function like enabling a register, enabling a counter, selecting some path through a mux, and all kinds of things. So that is the function of the controller. As at the beginning of the lecture I said, don't confuse it with the way you write a VHDL or Verilog code and say the finite state machine do a comparison or count or make anything. It just makes some decision as to go to some particular state, produce some output to control the data path. Okay, it does not do absolutely no data computation at all. Okay, everything is done by the data path combination circuit, that should be understood well. So we also talked about the Moore and Millet machine, and many a times like there is a possibility, like we have seen the output is generated as a function of the present state, but in principle we can generate the output as a function of the present state and the input. It is convenient, it has some advantages in some specific cases. It cannot be done just outright in all cases, but in some cases which we will see where it can be generated, the output can be generated as a function of present state. Many times textbook treat as two machine, one is a Millet machine and the Moore machine, but as I said it is very like these are kind of textbook cases with one input one output. So it is very easy to categorize like that, but in real life there are a lot of inputs, lot of outputs. So we talk about Millet output when the particular output is a function of the present state and input, and the Moore output when the output is a function of the present state and input, and we need to kind of internalize that process of thinking in terms of the Moore and Millet, because if you get used to the Moore kind of output like working that in your mind, then sometime you may miss, and because the Millet output could be advantageous, so you should check whether a Millet output can be designed. So let us come back to the slide. So this is the 3 block view. As I said, you have a state variable flip flop, a next state logic which is decoding the next state from the present state and input, and the output logic decoding the present state and input. You should keep this in view. We use it for analysis, we use it for coding, maybe use it for solving the issues to think, and so 3 block view is a good kind of abstraction. And maybe as I said, if you look at these 2 blocks, both get the same kind of input, present state and input, so we could combine these as a logic. So that is shown here. You have a logic which comprises of the next state logic and the output logic. So this logic input is the inputs, various inputs and the present state, and there is a part which decode the next state, there is a part which produces various output, and this is also useful for analysis and the coding and all that. So both should be kept in view. The textbook shows either some textbooks show the earlier view, some shows this view, it does not matter. The understanding is important whether but these kind of pictures, keeping that in mind, will help to sort out the issues, analyze and so on. So that is what is pictured here. So let us come to today's kind of part. So let us analyze the timing of the state machine, and if you take this structure, 2 block view is kind of easy to kind of analyze. So here, because it is identical to the counter, only one part is an output is an extra thing. So when we work out the maximum clock period, there are 2 sets of path we have to analyze. One path is same as in counter. When a clock comes, the Q changes and it kind of propagate through the next state logic, and the next state gets ready before the setup time. Okay. So that is what is shown here. You have, when the clock comes, this present state changes after a TCQ time, because from D to Q it takes so much time to change, then it propagates through the next state logic. So at this point the data comes here. Okay. But we know that before the next clock edge comes, for the proper operation of the flip flop, this has to be set up before the next edge. The data has to be there some time before, called setup time. So the clock period from this edge to the next edge should accommodate the TCQ plus the next TNSL is the timing, the propagation delay for the next state logic, and the setup time. So the clock period should be greater than the sum of TCQ, TNSL and TS, and of course we give a margin. It is not that even if we take the maximum values, it is better to give a margin, and we many a times doesn't worry. There are so many changes, the temperature change and the power supply changes and all that, the power supply voltage changes, the timing can change. So it is always better to give a little slack or a little margin, so that it does not violate the clock period requirement. But here one other path is there, like you view at the same time when the clock comes, you see after TCQ the present state changes, but for the output it takes some output logic delay and output changes here. Okay. And it looks, at least when you add up some, here we are adding up 3 terms, but here we are adding 2 terms, but it need not, like it does not matter. Maybe the output logic delay can be greater than the next state logic delay plus the setup time. Okay. So we have to consider the maximum delay of both the paths, like that is what I have written here. T clock min is greater than max of 2 paths, the red path, which is the red line here, this path, register to register, or a register to output. Okay. Suppose assume that you add up here, you get say 3 nanosecond, and you add up this, then you get 4 nanosecond, and if you choose the 3 nanosecond for the clock period, then the state changes happen properly, but the output does not change. Before the output settles, the state is changing. So output never get to change properly, there could be glitches and things like that. So you have to consider this. Okay. Now once again, and F max is the less than 1 by T clock, and the slack is like you subtract the maximum path. I have shown only this from the clock period, but the maximum path from the clock period you get the slack. But one point you should understand, when you put a picture like this, we assume the output is coming here. Okay. Like in this analysis we do not know where this output is going. So we have treated this as the endpoint when you put such an expression, but in real life if this is a controller, this goes to somewhere, maybe this goes to another registers the data input, or it goes to some combination circuit like a select line of a mux, and that mux output goes to a register. So in such cases, for the completion of analysis, you have to consider complete path from this register through the output logic, through the whatever is the combination circuit following, up to the next input of the register. Okay. The complete, then only you will get the picture, but when I put a picture like that, I have no a priori knowledge of that. That is why I am writing like this. But if there is a path terminating on a register, you have to consider the whole path, okay. And in a sequential circuit definitely it will terminate in some kind of register other than very simple kind of indication or something like that, like some lighting up a LED or something like that, then maybe this analysis is helpful. But that you should remember that it goes somewhere, and when you analyze, you have to analyze from this point all the way up to the end point. That you should keep in mind. And so ultimately you have if you find, you add up together, if you find that the clock period cannot accommodate it, then you have to increase the clock period, or the frequency has to be reduced to accommodate this whole path to make it work. But the another thing is the hold time violation, that we know that at this point when a clock comes, the data, the rule is that whatever the data was there, it should remain there, it should remain there. When a clock comes, the data was there, that should remain there for some more time, called hold time. So but we know that when a clock comes, the data here, the old data here will change only after TCQ plus T next stage logic. So we take the minimum, that means the data will change from TCQ plus T next stage logic, but there is a maximum value and the minimum value. As far as hold time is concerned, the minimum is the critical kind of timing. So the TCQ min plus T next stage logic min should be greater than the hold time, the maximum hold time. So that is to violate the hold time, and as I said, there is no clock period here. If it violates, you have to increase the combination delay. Why there is no clock period is that it refers to the same clock edge, because we are the data, like a clock edge comes, the data here has to remain there for some time, but the data changes at this point due to the same clock edge. So we are not like in the clock period analysis, we are going from the one clock edge to the next clock edge, but in a hold time violation we are considering the same clock edge. Like a clock comes, the previous data when the clock comes has to remain there for some time, and we are working out because of the same clock edge, the data here, how fast the data here changes. It propagates here, it propagates there, and it changes there. That is why the clock period is not there. So if the hold time violation happens, then it is it's nothing to do with the clock frequency. It is you have to increase the combination delay, and normally you put two like the pictures will show some two inverters back to back you put, then this problem is solved. So that is the timing analysis of the state machine, almost exactly similar to the counter, and the timing analysis of all sequential circuit looks same, but I just wanted to reinforce that fact. Actually need not be considered separately, but then again for the learning that is useful to reinforce and consider this extra path which cropped up. And if you consider maybe the 3 block view, that could have been maybe little easy, like here you have one set of paths here and the other set of paths there. So whichever way you look at it, it is all same. So that is the timing analysis for the state machine. And okay, this is the part which I have already discussed. So let us look at how to go about designing a controller. And many a times when you design a controller, you have some description, like if you have a CPU, what you have is a data path and you have some instructions, and you know what the instruction does. Okay, you may write it in text what the instruction does, and now you have to convert that instruction into steps in data path, how the data path operate in terms of the steps of data path. That is again a maybe textual description, but we are already bringing in some sequences, some steps or sequences, and that is very useful because we are designing a sequential circuit. So if we can, the moment from an instruction to kind of steps or sequences is already a we are coming near to the control algorithm. Now the next step is to write a waveform, that is what we have done. We have described like when we took the add instruction, we have textually described the sequences like moving something, selecting something and so on. Then we put a waveform, then so that is what is required now. So like when you design the control algorithm, the first step is always writing the various sequences, writing the waveform, and the ultimate aim is to design the next state logic and the output logic. So for us the third step is that you convert this waveform, convert these sequences into states, and it is almost straightforward because each sequence need a state like that. Some input comes, then it goes to a sequence, or some input comes, it go through 2 or 3 steps or 2 or 3 sequence. In the case of add instruction, one instruction came and it just went through some 3 steps, but it may be different that like some input came, it goes through 2 steps and it check for some other input, then it make a decision to go to a step A or step B and continues and things like that. Sometime it comes back and so on. So that is designing a control algorithm. So let us look at the slide. So basically you will have to decide the sequence of operation for various input combination, and it is not it cannot be done easily from a waveform to a next state table or an output table or the truth table of the truth tables of next state logic and the output logic. And many a times we are not clear, there are a lot of possibilities, like in an add instruction we have moved A to TR1 and B to TR2. We could have done the opposite, we could have moved the A to TR2, B to TR1. So when you work out a sequence there are various other possibilities, like there is no it is not very clear at the beginning what all sequences, what is the best minimal way of doing, efficient way of doing these sequences. So you have to literally work out, we have to work out, and we cannot work out in terms of the truth tables and so on. Okay. So we need as humans we are good at some kind of graphical tool to think, and that is what happens in a software. You know that there are flow charts or pseudocodes which helps you in thinking, like you have a vague idea of an algorithm and you are formalizing it in very clearly, then graphical tools will help. Okay. So we have a set of sequences, set of waveforms, and then we have to convert that in terms of the state of the controller, transition of the controller depending on various inputs and outputs produced at each state. So all this can be done better done graphically. So as far as a state machine or controller is concerned, there is a graphical tool similar to a flowchart in software, and that is called state diagram. So state diagram helps you to visualize the control algorithm in terms of the state machine behavior. That is what is basically done. So let us look at that is what written here. We use a graphical tool to basically to visualize. It is for human being, not necessarily for kind of the languages or the software tools, but essentially we will translate those kind of the diagram, what is in the diagram, to kind of equivalent description for various languages. So that is a state diagram. So basically what it means for the state diagram is that what we are trying to represent is we have to represent the states, we have to represent inputs, and the state transition, like you say a particular input came in a particular state, then it transit to another state, okay, and in each state it produce some output. So that is what state diagram captures, various states, various transitions, which is the states are represented as an oval or circle. Maybe like oval is better because the circle is very difficult to draw. A proper circle, oval may be better because we can write something within, and at least even if normal human beings draw a circle, you will end up with an oval. So maybe we can use oval, and transitions will be shown as arrows from this one oval to other oval, and we have outputs, various outputs. In real life there could be 5 to 20 outputs for state machine, that is written somehow connected to the state, because the outputs are associated in each state. So basically that is the state diagram, and we have to, from the state diagram we have to derive this next state logic and the output logic after doing the state assignment, okay. That is the basic idea. So let us look at the state diagram. So once again keep this structure in view, the state flip flops, the next state logic and the output logic, 3 block view or the 2 block view, and then let us go to the state diagram. So in the state diagram we have states, transitions and outputs. So let us look at the states and transition. So this is called unconditional transition. That means the controller present state was some state, maybe S0, like if we have 3 flip flops it means maybe 0 0 0, okay, 3 zeros. Unconditional transition means when the clock comes the state go to the next state, like it transit from 0 0 0 to 0 0 1, or you go back to the diagram, it means this present state was 0 0 0 0 and we decode it to produce some output. A clock comes, irrespective of the input, the present state is decoded to the next state 0 0 1, and the next clock comes, that is loaded there. That is the meaning of this. And you are in one state, the controller is in one state, upon the clock it transit to the next state, that is there is no condition, it happens on the clock, there is no input condition. So there could, like unconditional transition, there are conditional transition. That means the state machine present state is some state called S0, and now there are inputs, you look at here, this is S0, there are a lot of input. One input is called enable, and if enable is 0 the next state is decoded as something. If enable is 1 for the present state, the next state is decoded as something else. So depending on the input value the next state changes, and upon the clock that the present state becomes the next state. So that is shown here, like the present state is S0, and when the next clock comes, if the input is enable is 0 then it goes to S2, enable is 1 it goes to another state called S1, and the outputs here and outputs here are different, so different action happen. So it is like in a flow chart you are making a decision, depending on some input you branch to some state and do something else totally different. Maybe you can imagine in the case of kind of CPU example, say this produces, this is the state for fetching the instruction, and depending on the instruction, type of instructions, like say the move instruction you come here, say the add kind of computation instruction you come here and do something, and so on, okay. So various you can connect it with the kind of applications, kind of scenarios this can fit in, okay. Now there is another very useful structure which is useful here. The present state is S0, and there is an input called enable, and it could be called anything, and as long as that input is 0 it remain in that state, and when that input, like however many clock comes, it remains there, and when that input becomes 1 it transits to another state. So you can say it is we are waiting for something to happen, okay. So like you can imagine that the controller initialize something and you are waiting for that some signal from the circuit, or you use there is a data path which is doing some computation, you enable that you kind of started that computation, you are waiting for it to get over the state machine. When it gets over it is continuing and doing something like that. So very useful thing, it wait for some signal, wait for something to happen and it remains in that state. So it means that the state was some state and it is waiting for some input to go high from the data path. Data path is doing something, is waiting for the state machine is however many clock comes, it can remain in that state for a day if that input does not come. So it just remain there in S0, when that signal comes it transits to S1 and do something else. So that is what is shown here. It's a conditional transition, so many times it is called wait and go, like you wait for something then go to the next state. So only these are the kind of 3 state transition possible. There could be variation of this, multiple transition on multiple more than one signal. You can imagine there are 2 signals controlling, then there could be up to 4 transition depending on maximum 4 transition and so on. So let us look at the output. Now we have to handle in the case of output both Moore and Millet output. This is the Moore output I have shown here. In this state, say there is a signal called read bar which is 1 and latch 0, okay. So that is what is shown here, and this is associated with this state. So it essentially means that the S0 is decoded to produce read bar 1 and latch 0, and in this state the read bar is 0, it is transited, like it is changed from 1 to 0 and latch is made 1, and maybe in the next state the latch is 0, then you get a pulse on the latch for 1 clock period duration. In the case of Millet output, then you have this latch as a conditional output. So here you see the FSM is in the state S0, it is waiting for this enable signal to happen, and when enable signal, and as long as it remains in this state the latch is kind of 0, because latch is 1 when enable is 1, that's a condition here. So when enable comes it does 2 things, it transits to next state upon the next clock, and in this state itself when the latch becomes enable becomes 1, the latch becomes 1. So that happens in this state before the state changes, and this means in the next clock when enablers become 1, in the next clock the transition happens, and you know that it has to be set up much before for the transition to happen, because we have this, if the transition has to happen then that enable has to come some time before the setup time and the logic delay, then only the transition can happen. So the enable in this case has to come properly much before. So when this controller is in this state and the enable comes before, during that duration the latch will be 1. So that is the meaning of it. We will see the timing of the Millet output later, but that is how the state machine looks like, okay. So let us take an example state diagram, very simple state diagram, and this is not something kind of arbitrary state diagram of a controller. This is the state diagram of a multiplier, which we will take as a case study later, but I just want to kind of highlight how a real life state diagram looks like. So it is very simple state diagram. So this we have 3 states, and you see S0, and this shows that at the power on you have to bring it to a starting state because we have to start in some known state. So we will see how to bring a controller to a power on state, and then it is waiting for a start signal. So here this is the output, there are 4 output called P reset, kind of shift signal, load signal and select signal, okay. And upon the start, so it shows that it is waiting for a start signal from outside. Upon the start, so this is the kind of power on initialization, everything is made kind of inactive. Upon the start signal it comes to a state called initialization state. It initializes the data path, okay. So reset is made 1, some loading happens in the data path, then it goes to a computing state where number of iteration happens, okay, and it is waiting for that iteration to end. We will see how that happens. So it is looking for the computation to stop, and that is called a max signal. As long as the max signal is low, the computation happens, and this is the kind of shift signal is 1 for whatever reason, we will see that later, and it is selecting some path in the data path, and when the signal comes from the data path it goes back to the starting state waiting for the next start signal and so on. So this is a kind of real life state diagram of a controller, of a multiplier, and you see that the inputs decide the state transition, and there are states, 3 states, and for each state there are kind of output associated. Most of it is more output, but you see this select line is a milli output because select line is a function of some signal called R0, which is not shown here. It need not that it need not be the case that some of the input coming to the state machine need to produce the milli output, you know, it is not required. It can be something else but which is related to the data path we are controlling. Naturally that has to happen. So the moment you do this the state diagram, then we can write the next state logic and output logic, that is the most important thing. So like look here, and before going that we have to assign some state kind of state assignment that need to be done. So here if you do binary encoding for 3 states we need 2 flip flops, okay. So let us assume the states are like you have 2 flip flops Q1 and Q0. Let us assume a sequential state assignment saying that this is 00, 01 and 10. So how does the next state logic looks like, you know, it start like that. At the power on, next state is the present state is 00 and input signals are there. When start signal is 0, the next state is 00 itself, it remains there. When the start signal is 1, then the next state is nothing but 01. So looking at the state diagram you can write the next state table. So the moment you have the state diagram, then you can write the next state table. Same thing is true of the output table, the truth table of the output logic or output table. Like you see here in the state S0 the P reset is 0, shift is 0, load is 0, select is 0. But when it comes in the state S1 or 01, reset is 1, load is 1, rest are same, okay. So that can be easily written in a table. And one thing I should mention that many a time some textbooks will show that like for kind of brevity or for a concise representation it will show only the signals that change, okay. That means do not write everything, you have 10 outputs, do not write 10 outputs everywhere. See here if you see reset and load only changes, this remains, so do not write it. But this as far as the figure is concerned it will be much neater, but when you develop a next state table or output table or write a code to do this, you can miss that point. Don't write, you will get into a lot of trouble. So I don't suggest that you do such a thing. Okay, there are clever ways to kind of circumvent that problem by initializing some default values and so on in a coding, but it's not a very good idea. So you should, it is better you write explicitly what are the outputs. Okay, I am warning kind of various pitfalls people or the mistakes people make when when you are designing the state machine. So let us look at the both tables, next state table and output table. So that is what is captured here, like this is the present state Q1 and Q0. We have two inputs, start and max, only two inputs are there, the start and max. So that is what is shown here, and we are decoding the next state, that is a kind of function of the next state table. So initially at the power on it is in 00, the present state is 00. When the start is 0, the max is don't care, we don't care about the max, then the next state is 00 itself, and when start becomes 1, max don't care, 00 transit to 01. And if you see the next transition, when you are in S1 01, there is no condition, it transit to 10. So when you are in 01, irrespective of the condition, the transition is made to 10, and again when the max is in, you are in 10, max is low or inactive, then it remains there waiting for the max to become 1, and when max is 1 it transit to 10 is transit to 11. So you basically get two equations for D1 and D0. Normally we form the equation in terms of the Q1 Q0 and the inboard, minimize it and all that, not required. This can be easily coded, and the tool, synthesis tool, will do the optimization and kind of create the necessary circuit to implement the next state logic. But mind you that this state diagram, whatever the state and transition part and the next state table is equivalent. We have written the table from the state diagram only. So many a times in design we need not write this table, we describe the table in terms of hardware description language looking at the state diagram. So the moment you design the state diagram, the controller design is over, we describe this next state logic, that's all in hardware description language, then the design is done. So let us look at now the output logic, and as I said, it is not good to kind of some textbook will show you that you even write the output here, various output, and you say for 00 what are the outputs, but then it is very crazy because this being a next state logic table, the 00 is repeated twice. So you are forced to write the output repeated twice, and we have no way to know whether the output is a function of the present state only or input, and there is confusion, and sometimes people write the input condition on top as a kind of row label, this as a column label, and the resulting state and all that. In that case it cannot be combined at all, but I suggest that you don't complicate, use the symbol method to represent it, separately represent it conveniently, at least for you to study. Nowadays in real life there is no need to write a next state table or an output table. So this is the output table, like present state, it is a function of the present state is 00, then you know that everything is 0, all the outputs are 0, 01 this reset and load is 1, and 10 the shift signal is 1, and select is R0. It is not shown here, but maybe you can show the input as also in the table, does not matter, but then that is the way it is. Again this is exactly equivalent to the state diagram because it specify for each state the output, so kind of the output logic is kind of identical to the state diagram. It is enough we write the hardware description looking at the state diagram. The moment you have drawn, everything is done and captured, you can describe in a hardware description language from the like we can describe the logic, next state logic and output logic looking at the state diagram. That is enough for the design. So that is it's about the state diagram and the next state table and output table. So like before going further, we will start with a case study. At least I will mention the scenario and do the design in the next class. So just now we have seen we have done the timing analysis of the state machine. Basically the register to register path and register to output path possibly extended to another register path, hold time annihilation. Then we have seen that we have to go from the textual description to waveform by coming out with a sequence of steps and ultimately translate that sequence of step into the state of the state machine and various transition and various output it produces. And to many a times, as I said, control algorithms are not easy to kind of design because there are various possibilities we need to work through. It is not that straightforward you get the algorithm. Maybe there are like when you work with the CPU case, you will find that there are common part, like you might come out with a state diagram for various instructions. Then you find that there are instructions for which the number of states are equivalent. So you can combine them together and all that. So it needs a lot of kind of work on a piece of paper, and the graphical tool is convenient. So so we have a graphical tool called state diagram which represents the state, which represent the state transition depending on the input, and which also shows various output. So we have seen some kind of the state represented by oval, arrows represent the transition. We have seen unconditional transition where upon the clock a present state goes to the next state, and conditional transition where depending on input it makes some branching, 2 or more branching. And there are also wait and go structure which wait for a particular signal or a group of signal to change the state, then goes to the next state. We have seen Mealy and Moore outputs. Normally the outputs are shown connected to a state, and the Mealy output is written as a function of the input. That input need not be part of the state transition, that you should keep in mind. It could be some separate input coming from the data path. And I also said that don't use shortcut when you describe the output. Don't write just the output which changes, so that there is no confusion. And we have seen an example state diagram, and we have tried to work out the next state table and output table from the state diagram. What turns out is that the next state table we write all the information is in the state diagram, output table we write all the information is in the state diagram. So the moment somebody draws a state diagram, the control algorithm is fixed, and the everything required for the state table, next state logic and output logic is there. So it is enough in our methodology, we code this in a hardware description language, the thing is done. So I think kind of you get a picture of kind of what is the controller, what is its structure, how it is designed, what are the tools we use, graphical tool we use to design the controller. And now we will illustrate. It's not that unless we do some somewhat real life scenario, this may not become very clear. So I will take a simple example where the concentration is on the controller, not the data path. So because if you put a data path, then we have to design the data path. So I have taken one example where there is not much of a data path, but then that there is a controller which is a very it's not that I cook up something very simple. It's whatever I describe is a very useful thing in the next lecture, the case study. So our idea is that we go from the word description to all these procedure all the way up to the next state logic and output logic. So you can relate the older step, that in the present scenario that we are not doing everything by hand. Most of it is done by the tool, but there is a part where the designer's involvement is quite high. So I will illustrate every step involved in the design, whatever the designer does and even the tool does, okay. So that you get a clarity understanding. That is what is the lecture is, this course is about. I want to bring the concepts very clear in your mind, what the designer does, what the tool does, without much relation to a particular tool. As we go along I will show all that thing in some kind of design tool. Definitely that will be illustrated, but this case study, this is a kind of simple case study to start with. We will discuss in the next lecture. So don't take it very lightly, these kind of topics. Please go back, look at it, analyze it and learn it well. It should be clear in the mind, it's not that. So you should work out in the mind and you should be able to visualize all these in the mind, then, because when you design complex thing it will be good if you can kind of design these things in the mind. So I wind up the lecture here. Thank you and wish you all the best.